How does capacitive reactance affect current flow? Imagine a circuit where a capacitor is connected to an alternating current source. You might wonder how this tiny component influences the flow of electricity. Well, capacitive reactance is the key. It is the opposition a capacitor offers to the changing current in an AC circuit. This opposition depends on how fast the current is changing, which is related to the frequency of the AC signal. The higher the frequency, the less opposition the capacitor provides. Conversely, at low frequencies, the capacitor resists the flow more strongly. The formula for capacitive reactance is 1 divided by 2 times pi times the frequency times the capacitance. This means the reactance gets smaller as the frequency or the capacitance increases. When the reactance is low, more current can pass through the capacitor. When it is high, the current is limited. Think of it like a narrow gate that opens wider at higher frequencies. The current in an AC circuit that passes through a capacitor is related to the voltage divided by the capacitive reactance. So, if the reactance drops, the current rises for the same voltage. Interestingly, the current in a capacitor leads the voltage by 90 degrees, which means it reaches its peak before the voltage does. This phase difference happens because the capacitor stores energy in an electric field when the voltage increases and releases it when the voltage decreases. This process allows the capacitor to act like a temporary energy reservoir without dissipating power as heat. In practical applications, capacitive reactance is used in filters to block low-frequency signals and pass high-frequency signals. For example, in radio tuning circuits, capacitors help select specific signals by controlling how much current flows at different frequencies. Understanding how capacitive reactance affects current flow helps engineers design better circuits for communication, power management, and signal processing. It also explains why capacitors are essential in managing energy transfer and filtering unwanted signals in many electronic devices.